All right, so what I want to do here is I want to finish up this example we were on, and then that's going to close up chapter 7, or what is this, module 6, I believe, on friction. And then, I mean, you should be able to have done most of your homework already, just from, well, assuming you're reading as we're covering the material. Remember, the reading is, I can't read for you. So I can give you the summary slides, but that's pretty much it. And then we're going to start. Well, what we'll do is we'll talk about the test. I'll go over some of the issues that I saw and some of the solutions, and then we'll start chapter 8, which is module 7, which I linked in here. And we may not get to this until Wednesday, but I've got all the PowerPoints, the PowerPoint and the handouts. There is another homework for chapter 7. When is this due? Oh, sorry, module 7, chapter 8. Okay, so I put this for next Wednesday. So we'll see how much we get done. Again, I'll move things as needed, but there's no reason why you can't start working on the homework. You know, just because we haven't covered an entire module in class doesn't mean you can't do some of the problems in the homework. In fact, the old way, the last instructor used to have it broken down. They would give the homework I think every other day, it looked like. And you'd have to turn it in. But I decided, you know what, I'm just going to do chapter at a time. And they wouldn't grade everything. I like to go through it and see what's going on. All right, let's see. There's my document camera. All right. So we had left off here. We had a cylinder with a mass of 250 kilograms, which, remember, you've got to convert for forces, right? A mass needs to be multiplied by acceleration of gravity to get a force, right? So weight is mass times gravity, and weight is a force. So we looked at this then and we said, okay, this is once wrapped around the pipe once, right? So it looks like this. So now we're going to look at part B. We're going to say, okay, now we're going to wrap this cord around the pipe twice. And the coefficient of friction is still the same, right? Static friction 0.2. The thing that's changed now is the degrees, the angle. So let's see what that looks like. I never know how to draw this. You know what? I think I'm going to get a different color for the pipe. I'll do the pipe in pencil here. So let's see. We've got a circle. And that's the pipe. And our cord is wrapped around it twice. So we've got one wrap, and then, oops, two wrap. This is supposed to be in contact. I'm just kind of showing how it goes around twice, right? Now, oops, I gotta move that up. If I look at what's happening, we're looking at the same scenario, right? We want to know what's the smallest force, F, that we need to support the load. So now the load is over here. We have the weight. And this is our force. And inside here again, you got to think about, okay, which direction am I looking to prevent slip in, right? And I want to prevent slip from happening this way. So that means the friction force is acted in the opposite direction. And because you have this time, the cord goes all the way around, right? Your force of friction is all the way around this thing. In fact, the force of friction acts pretty much anywhere where the the rope contacts the pipe, right? Which is going to be, it's going to be 1 loop plus a half, right? So 540 degrees. So 2 wraps around the pipe, right? So that's 360 plus 180 gives you the 540 degrees. We need to work in radians. So 540, oh, 540. And you multiply by pi over, say, 180 degrees, and you wind up with, I'm just going to leave this as 3 pi radians. All right, from the same formula we used above, right? TL over TS equals e to the mu theta. Let's figure out which one of these is which. They're going to be the same scenario, but let's understand why again. Go back here for a minute. Well, you know what? I think I'll talk about that in a minute. Your small and large tensions, right? The large tension in this case is the weight, because this is the one that we're trying to prevent from slipping, right? We've got the weight, then we've got friction opposing this, and this tension is going to be smaller, right? Because this is a small tension because you've got friction helping you, right? Friction is acting in the same direction as the small tension. So let's see, we're going to rearrange this equation just like we did above, and we're going to find that TS is equal to, we're going to have TL, oh, I already did the math up there, e to the negative mu theta. All right, that's how we do the same thing up here. I just skipped the intermediate step here. And this is going to be equal to, what do we got for TL? We've got 24, 52.5 newtons, right? The load hasn't changed. It's still a 250 kilogram mass, which gives us the 2452.5 newtons. And then here we've got e to the negative. In this case, mu is still 0.2. And our theta is 3 pi radians. Remember that angle theta is in radians. So from this, we see that TS equals 372 newtons. All right, so let me just make a quick little table over here. Number of wraps, force required, what do we get? We got 13. I'm going to round this up to 3 significant figures, 1310 and 372 newtons, right? Which makes a lot of sense. If you wrap this around the pipe one time, you need more force. You need to apply more force over here to keep this weight from slipping than if you wrapped it around twice, right? So that's what friction does for you. It helps you support a load in this scenario. I just want to go back real quick. Are there any questions specifically about this problem? And then I want to go into the PowerPoint, point out one thing. There's no questions. In this scenario, Okay, this is the scenario, right? So this is the scenario where we want to lift the weight. So you got to be careful, right? The example we just did is keeping the weight from falling. If we want to lift the weight, right, now our motion is in the other direction, right? We want our load over here, or our large weight is the force we're applying, our large tension, and our small tension is now the weight, right? Because now we want to pull this way, and friction is going to oppose our motion to lift the weight. So you got to be careful choosing which tension is the large tension and which is the small tension. And that depends on the physics of the problem, right? What are you trying to do? Are you trying to prevent the weight from slipping, right? Are you trying to prevent this from falling, or are you trying to lift it, right? Two different scenarios. All right. So that's pretty much, oops, friction. That wraps up all of module 6. Let me go to talk about the test here a little bit. This is the key. Let's see, I've got a little post-it note to give you the averages and stuff. Yeah, I always like to do the average with and without zeros, because some people just don't take the test. And it's like, well, I don't know why you did that. But without zeros, the average is a 57. So if you're not happy with your grade, the maximum was 106. So someone did get, well, more than one person got the bonus, or at least part of the bonus. So I did give bonus points out. It's just that no one got a perfect grade on everything. So there's no 110s, but there was 106. So that's, I think this person got the whole bonus, but missed some points somewhere else. Let's go through. Oops. I'm not going to go through the multiple choice unless you really want me to, but I want to quickly just show the, now I can't remember on the actual test. Let's see, let's go to the test, because I want to show you how it was phrased. I printed it out differently than I actually wrote it in the, oh, that's not what I want. I want the test here. All right, I was close. All right. Part of this problem was to draw a complete and accurate free body diagram. The free body diagram will be uploaded as part of your scanned work in the last problem. So you needed to submit a free body diagram, and it needed to be complete and accurate. You can't just put some numbers in here and call it a day. The point of this problem was to be able to do both, right? Draw the free body diagram, but also convert these distributed loads to point forces. So this is kind of, again, my notes here are a little bit all over the place. But this is what your first of all, your free body diagram, you should start with drawing this out, right? And you should start by putting, I've got two forces at A, which is a pin joint, right? And one force at B, which is a roller. And then I've got some forces that I can't put on here yet, but I've got to take the distributed loads and convert them into point loads. So for the rectangular section here and the triangular section, we can convert those into point forces acting through the centroid. And what are the centroids? Well, for a rectangle, it's right in the middle, right? Right in the middle of the 2 meters. So I just take the 600 Newton meters, or newtons per meter, multiply by 2 meters. I got 1,200 newtons of force. That's my force R for the rectangle at 1 meter. All right, so I can draw that on my free body diagram, and I can label the dimension. So some people just took this diagram, put it down here, labeled it, and then drew some arrows in without any dimensions. The purpose of a free body diagram is to allow you to solve the problem. This means that any information you need to solve the problem needs to be on the free body diagram. If you don't know the dimension or the distance of the 1200 Newton force from either the sides or one of the sides, you can't solve the problem, right? If you just know the distance here is 2 meters, but you don't know where this is, the free body diagram doesn't help you solve the problem. The next one was the triangle. I've got a 600 Newton per meter force that tapers down. So it's 1/2 base times height. The 3 meter base times the height of 600 Newtons per meter gives you 900 Newtons. For some reason, a bunch of people put 450 Newtons there. And it's like they divided it in half and then thought they didn't divide it in half. So 900 Newtons, not 450. The centroid of a triangle is B/3, right, from one end. And this one was fairly straightforward because from B, it's only 1 meter. That means from A, it's 3 meters away. So you wind up with a free body diagram that looks like that. All right, truss. This one was very interesting to grade as well. I broke it down into parts. Well, I broke it into sections. And for part A, you did not have to break this thing apart. Some people were taking this thing apart, trying to figure out the reaction forces, and that's not the way you do it, right? This is just the free, part A is just getting the free body diagram of the truss, right? Let's go back to the test here and see how I actually phrased it. It says, you must provide free body diagrams for each part of this problem, and you must use a designated method to solve each part in order to get full credit. So for part A, it was just the standard, free body diagram. Determine the reactions of the supports A and D. And I told you what P1 and P2 were. Where's the graphic? Here it is. So P1 and P2, you were given that information. 1,500 and 600 kilonewtons. So that looks like this in the free body diagram, a very, very messy free body diagram, but I've got my lengths in here, right? I know these are 3, 4, 5 triangles. And I have my reaction forces. A is a roller and D is a pin. So D has 2 reaction forces, A has 1. Don't forget your loads, right? P1 and P2. You could do this a few different ways. I did it, some of the forces in X is 0. This is, I gave 3 points just for this. If you recognize there was no force in the X direction. So that was easy. And then the free body diagram I gave some credit to as well. Then you do one of these two, only one. Some of the moments about D or some of the moments about A. And I can't understand, a bunch of people put their variable in here, but switch the values. So the sum of the moments about D is equal to 0 means what are the moments generated by these forces about point D, right? And we've got a 600 kilonewton force at 3 meters away, right? This is counterclockwise moment. We got a 1,500 kilonewton times 6 meters. That's again counterclockwise. And then we've got, this is supposed to be an A. Again, these notes were more for my own grading, but A is pointed upward in our diagram, minus A times 9. So I've got, now you could have drawn this the other way and it just would have been a plus A, but you still would get the same answer. These are all equal to 0. The sum of these equals 0. A is the variable you're solving for, not D. You're taking the moment about D. A is your variable. So A is 1200 kilonewtons up. Now, if you did this the other way, sum of the moments about A equals 0. That's what are the moments generated by these forces about point A? And so here we can see again, we're using a counterclockwise is positive, right? So the 1500 kilonewtons is generating for at 3 meters away. That's a clockwise moment, right? It's a negative. Then we've got 600 kilonewtons at 6 meters, and that's also a clockwise moment. And then we drew D pointing upward, so it's dy times 9. That's a clockwise moment, right? The positive and negative signs don't come from the direction of the forces. They come from the rotational moment about the point of interest, right? So notice here, the 600 kilonewtons is at 6 meters from A and generates a clockwise moment about A. Here, the 600 kilonewtons is 3 meters from D and generates a counterclockwise moment. So that's why the signs are different. And then you solve for dy, and dy is 900 kilonewtons. Now, you could have done them together this way. Now, if you only do one of these, you use sum of the forces in y, right? Sum of the forces in y equals 0. You've got A minus 1500 minus 600 plus dy. A plus dy is 2100. So if you found A, you plug that in over here and you get dy. If you found dy, you plug that in here and get A. Overall, those were the forces, 0 kilonewtons, 900 kilonewtons up at D, and 1200 kilonewtons up at A. So this is where it got a little dicey trying to grade. Mostly, if you got these wrong somehow, you could have done the rest right and gotten full credit. Because I use your numbers and go through and figure out if you did the method of joints correctly. In fact, there's someone that actually put A in the wrong direction, and so as long as they did everything correctly, I gave them full credit, even though their answers were reversed. So let's look at part B. Part B says, use the method of joints. Find the force in members AE and AB. State if they're in compression or tension. So we would start with point or joint A, because this is where we have a known piece of information. We also have the least number of unknowns. You wouldn't start with joint B just because you want AE and AB. This doesn't tell you anything about AE. You have to work your way backwards. So you start with joint A. And this is actually a fairly simple analysis, right? You're basically doing a free body diagram of the joint. So you look at the joint A, and you say, I have 1200 kilonewtons acting upward. That's force A, right? The other forces we don't know. We're assuming they're in tension. Now, there were some people that did them backwards. They assumed they were in compression, or they just drew them out there and they figured it out intuitively, and that's fine. But if you're not going to rely on your intuition, you need to rely on math. So you need to specify some direction for these. In this case, I specified tension. So in my first analysis, I say, okay, I'm going to take the sum of the forces in the y direction equals 0. So I've got 1200 kilonewtons acting upward plus, now FAB does not contribute anything to the y direction, but FAE has a y component, and that's 4/5 of FAE, right? It's a force triangle. FAE has an x component and a y component. And the way I've drawn it, the x is to the right, the y is vertically. Now, again, intuitively should have told you. Some people just made the note, oh yeah, this has got to be pointing downward. I wind up solving this equation. I wind up getting FAE is negative 1500 kilonewtons. And this negative sign tells me it's in compression. So it's actually pointing downward. So I drew myself a second diagram. I wasn't expecting you to draw two diagrams, but it's good to keep track of things. I know I have 1,500 kilonewtons acting on point A, and I have 1,200 kilonewtons acting up on point A. Put A here. And that leaves me with this unknown FAB. So I do the force balance now in the X direction. What do I have? Well, the X component of this 1,500 kilonewtons is 3/5 of the 1,500 in the negative X direction, plus the FAB. And because I've drawn this and I've treated it in the negative direction, right? I see FAB is 900 kilonewtons, and that's pointing to the right, so that is in tension. So that's how you do part B, method of joints. Fairly straightforward, just a force balance on point A, pretty much. I mean, you did this with like the hanging flower pot, basically. All right, the next one was method of sections. So use method of sections, find the force in members EG, EG, EC, and BC. So you're cutting through this. And I did this both ways in case people did it two different ways. So let me show you what I've got here. This is taking the left side. And then you could also do it taking the right side. Let's focus on just the left side. I'm taking the left side of this. So I've got AE, AB, and EB. Those are the struts I have. This is the frame I have. EG, EC, and BC, I'm replacing with tension forces because I don't know how they're acting. And this is where it starts to get a little dicey if you try to think, oh yeah, I know it's going to go this way and I know it's going to go that way. If you guess wrong with too many forces, you start to have issues. So this is why the technique of drawing things in tension first is very helpful. The first thing I notice here is I've got two forces in the X plus a component of this in the X. That's going to give me three unknowns. So what can I get that I know? Well, I can do two things. I can start by eliminating these two forces and do some of the moments about E, or I can just look at the Y components and do it that way. So either one of these would be, okay to start with. Let's just take the sum of the forces in Y equals 0, right? We've got 1,200 kilonewtons up. A lot of people forgot this 1,500 kilonewtons. That's acting on the frame at that position. You need to include that there. So it's a negative 1,500. And then you have minus, notice the way I drew FC, right? Minus 4/5 FC, or FEC. And you wind up with FEC is actually 375 kilonewtons in compression. So that means FEC is actually pointing back upwards. And we'll use that information later on. Some of the moments. You can't do this problem by just doing some of the forces in X and some of the forces in Y. You run out of equations. We've got three unknown variables here. So you need to do some of the moments. And some of the moments about E is probably the easiest one to do, just because you eliminate these two forces from the equation. So this is saying what are the sum of the moments of all the forces about E is equal to 0. And what are the forces that I have? Well, these two forces are right at E, so their distance is 0. They're 0. Same thing with the 1,500 kilonewton force. That line of action passes through E. So that perpendicular distance is 0. So we're left with 1,200 kilonewtons and FBC. So FBC is 4 meters, or is this feet or meters? Yeah, meters. 4 meters away from E. And that generates a counterclockwise moment. That's why it's positive. Then we've got 1200 kilonewtons with a perpendicular distance away from E of 3 meters. A bunch of people use 5 here, and that's just not right. It's got to be the perpendicular distance from the line of action of the force to the moment point. So here we got a very simple equation. We solve for FBC. We see FBC is 900 kilonewtons. Now, FBC we assumed was in tension. We got a positive number. It is in tension. So now we've got FBC. We've got FEC. Now we just got to find FEG. So here's where some of the forces in X comes in. We've got FBC plus FEG. And we said FEC was in compression. So FEC is pointed backwards. Then the X component of FEC is 3/5 of FEC. So sorry about the mess down here. This was me. I don't remember what I did. I think I intended to do one thing first and then did something else. We've got 900 plus FEG minus, this is 3/5 times 375. So this 375 times the 3/5. This turns out to be an FEG of minus 675. Minus 675, the negative sign, that tells us that, well, we assume tension. We got a negative, it's actually in compression. So 675 kilonewtons in compression. If you did it with the right side, let's just go through this because it's the same, you get the same answers. I just want to show you how you can do it a little neater, apparently. So now this is looking at the right side of the strut or the structure. So I draw GDC, and I've got GE, CE, and CB. I'm cutting through those. I'm replacing those members with tension forces. And remember, you still need to have your reaction forces in there. D was 900, and at C we had P2, which was 600, acting downward. So some of the moments about C, let's look at that, equals 0. Oh, same logic applies here. You've got 1, 2, 3 forces that are unknown. You need to use 3 equations. You can start from Y, or you can start with some of the moments. If you start with, let's just start with some of the moments this time. Some of the moments about C, this eliminates a whole bunch of stuff that we don't need to worry about. And we're left with 2 forces because these all pass right through C. So their perpendicular distance is 0. We've got 900 times 3, right? This generates a positive counterclockwise moment. And notice the way I drew this, I treat it as a counterclockwise moment, right? FGE times 4. But when I solve this, I wind up with a negative 675 kilonewtons. That tells me that GE is 675 kilonewtons in compression, right? And that matches what we got up there. Next, we can go and use the sum of the forces in Y. We've got the, let's see, 900 up, 600 down, that's the positive and the negative. And then we've got the Y component of FCE, which the way I've drawn FCE is in tension. I've got plus 4/5 FCE. I do the math, I wind up with FCE is a negative 375, so that tells me it's in compression. And again, that matches what we got up there. You notice we should get the same answer, right? And then sum of the forces in X equals 0. So now we've got, let's see, the 675 comes from GE, which is compressing it. Right, so this is in compression, so that's a positive X direction. 3/5 of the 375, which the 375 we said was in compression, so that's acting down into the right. So that's a positive X. whether you get a positive, and then minus FCB, which is in that direction. And sure enough, we wind up with 900 kilonewtons, and that's in tension for BC or CB. This is the member, right? Are there any questions about this particular problem, number 13? Yeah, so I mean, if you go into your test, you'll see I have in the comment section, you know, what things might have been missing or where you might have gone wrong. And my intention was to go through it in class as well, so you'd at least have some reference video to look at. All right, this is a bonus question. This is basically taking my free body diagram from number 12, and I just redrew it here. This is the entire free body diagram. I don't need the original figure anymore, right? Because I have the free body diagram, and this has everything I need on it in order to solve the problem. I want to find the reactions and supports A and B. Now, I didn't give any credit for A x equals 0. That was just, I mean, that's by observation. And this is a bonus question, so I can do whatever I want on this. The first thing you do is you do one of the two, sum of the moments about A or B. Because what happens here? We've got two unknown forces in the y direction and two known forces in the y direction. If we do sum of the forces in y, we're going to get AY plus B minus 1200 minus 900 equals 0. And that doesn't tell us anything. We've got two unknowns. So we've got to get one of these. We've got to know one of them. So we can first start with sum of the moments about A equals 0. What do I have? I've got 1200 newtons acting at 1 meter away from A. And that's a clockwise rotation, so that's a negative. Negative 1200 times 1. Now I've got a force B, which I don't know. And I've said that's a positive moment, right? Positive counterclockwise at 2 meters away. So B times 2. This is the moment, right? Force times the distance. Now I've got another moment here, negative, because it's generating a clockwise moment. 900 newtons times 3 meters. So I have an equation here that I can solve for B. B is basically 1950 newtons upward. Now that I know B, I can solve sum of the forces in y equals 0. I've got A plus B minus 1200 minus 900 equals 0. I left this generically because I wasn't sure which one people were going to use first. A plus B is 2100 newtons, right? So if I know B, I've got 1950. A is going to be 2100 minus 1950. If I did some of the moments about B, I'm going to get A from that, right? Let's walk through that. Some of the moments about B. Well, A is a force that is generating a clockwise moment, so that's a negative, and that's 2 meters away from B. 1200 newtons will generate a counterclockwise moment, and that's 1 meter away from B. The 900 newtons is 1 meter away from B, and it's generating a clockwise moment, so a negative. So you can figure out AY using this sum of the moment about B as well, 150 newtons. And then if you did this one first, you'd obviously have 150 plus B equals 2100. You'd subtract and you'd get the 1950. That was pretty much the test. One of the problems it looked like people had was that they ran out of time. And I really don't, I gave you extra time on this because it was not in class, right? So we weren't limited by the 50 minutes. And I know you also had to upload your work. So I think I gave you, what did I give you, 70 minutes on this thing? There's no reason you should have run out of time on this. It seems like people ran out of time because they were spending a lot of time, an inappropriate amount of time, On the multiple choice, yeah, 70 minutes. The multiple choice, oh, this is because I switched order on my last test. The multiple choice questions are not, you shouldn't be spending 5 minutes on these questions each, right? Maybe 5 minutes total. This should be something that you look at and you recognize. If you're spending most of your test time on 20 points over here in the multiple choice, that's a problem. A lot of times people say, oh, well, it's not realistic, a time test and everything, but really it is kind of realistic. In a test, you look at the test and you're like, okay, I've got 20 points total for all the multiple choice. This problem here is worth 60. Number 12 was worth 20. Where do I want to spend all my time, right? You're going to have to do the same thing in industry. When you go out to work for a company, if you think they're going to give you one thing to work on at a time, you are going to be in for a big shock. And some of you know this already because you're working out there. But you're going to have to prioritize. And a lot of times you prioritize in the same way you have prioritized in a time test. You look at what is worth the most for my time. The same thing in industry. You're going to get some things that could be, okay, this small project can be put off until, tomorrow, but I've got to get this big thing done right now. And the points here are going to be things like, like satisfaction of your boss or satisfaction of the group that you're doing work for, right? Well, they're like, oh, I give this guy this important thing to work on, and he goes and works on this other stuff that's not important. Well, that tells people that you can't prioritize, right? Prioritizing in school, it's based on points, right? In reality, it's based on how important are these things relative to the project we're working on or the priorities that my group has, right? So you need to learn to prioritize. Don't spend all your time in a test working on the multiple choice, which is worth a total of 20 points. These were like 2 points each, 2 times 10. Did I put the question? Yeah, I did. I put the multiple choice, 20 points total. Question 12 was 20 points. Question 13, 60 points. And then extra credit was number 14. Now, it's good to get those multiple choice questions out of the way because it's a 20 there's supposed to be a 20 relatively easy points. But if you're spending time on the multiple choice and you're finding yourself going to the book and like looking through it because you don't know the stuff offhand, that's sort of a amount of time that you could be using to spend on questions 13 and 12 and 14, the extra credit, right? All right, I'll probably just stop here then. So next time I'll start module, I don't even remember what the module numbers are. Module 7, yeah, centroids. We'll talk about centroids next time. So go ahead and download that stuff. Be ready to talk about centroids. And this is going to help us relate to things like center of gravity when we get into that later on.